Hey guys, so I'm here to give you y'all's test review. I almost didn't do it, but I said no, let me get this test review out so that you guys can have this. So, anyway, test review. Sorry it's coming so late in the evening, but you know what? It is what it is. So, this test is thermochemistry. Okay, now remember, thermo, thermo means heat. Okay, it's talking about heat. Chemistry is study of atoms, so thermochemistry is how we look at how heat moves and changes during chemical reactions. Now, the very first thing we talked about in this unit was energy. Okay, now energy's definition is the ability to do work or produce heat. Now, if at any point, if you're writing this down to help you remember it and things like that, you can always pause the video if you need to write things down and my video is moving too quickly. But energy is the ability to do work or produce heat. The do work part is normally in physics. The produce heat part is the stuff that we really focus on in chemistry. Now, with energy, we have two different types. Okay, we have potential energy. Okay, and in chemistry, it's called chemical potential energy, and it's the energy due to the position. Okay, that position part is the potential of the atoms in the bonds. Okay, and so if you look at something like water, which is H2O, two hydrogens and one oxygen, we know that there is energy is stored in those bonds. Okay, and so that's kind of what we have going on there. Now, the second one is we have kinetic energy. Okay, now kinetic energy is due to the movement of atoms. Okay, and so this means if we have a high kinetic energy, okay, which Ke is just going to be kinetic energy, that means the atoms are fast. Okay, so something that's really high in kinetic energy would be like gases. Okay, they have a lot of kinetic energy when compared to the other ones. And if you have a low kinetic energy, okay, the atoms are moving slow, and so this would be our solids. Okay, liquids are kind of in the middle usually. And with that, kinetic energy plays an effect with how we measure that kinetic energy. So temperature, okay, measures the average kinetic energy in a substance. Okay, and so that means it's actually measuring how fast these atoms are moving. So we're like, well, Miss Nichols, I thought temperature measures how something is hot or cold or things like that. Well, let's look at this. Well, heat, okay, the definition of heat is the movement of energy from one object to another. Okay, and it always moves from warm objects to cool objects. So warm to less warm. Technically, there's no such thing as cold. You've heard me say that in class. There's only warm and less warm. There's no such thing as cold energy. You just have heat. So some things have less heat or less energy than others. But so that movement of kinetic energy, it's talking about that kinetic energy. So if something has a higher kinetic energy, some of it moves as heat towards another object. And if we add heat to something, if we increase the amount of energy it has, it's going to start moving faster or slower. So that's just kind of a misconception that I want to clear up there. Temperature measures how fast those particles are moving, and heat can make things move faster if we're adding heat, or if we take away heat, they can move slower. Now, with that being said, we want to look at two scenarios. Let's say we have two boxes, okay? Oh, and keep in mind, this is something we talked about. We have the universe, right? The whole wide universe is broken into two parts, your system plus your surroundings, okay? And your system is what you're studying, what you're looking at, and your surroundings is everything else. Okay, now in our box, okay, our boxes are going to be our systems, and the surroundings is literally everything else in the whole world outside of it. So we've got our surroundings. Now heat has the ability to do two things. Heat can either go into our system from our surroundings, or heat can come out of our system and into the surroundings. And so those are the two options. If heat is going into the system, we call that endothermic. Okay? Endo meaning in, thermic talking about heat, so endothermic. If it's leaving, like the box on the right, we call that exothermic. Okay? Now, one thing I forgot to mention is that the symbol for heat is Q, and so that means in this case, our system is going to have a positive Q because it's gaining that heat, whereas exothermic Q would be negative because it's losing that heat. And now, because this is chemistry, right, we need to say, okay, well, in terms of like chemical reactions, what does this mean? Well, we know you have reactants and products. Reactants being what you start off with, kind of like your ingredients, and your products is what's produced. And so if we look at this in a chemical reaction, you have your reactants plus energy to produce your product, okay? Now, in terms of like an example of this, if you think of maybe baking a cake, okay? In order to bake a cake, you need flour plus egg plus sugar plus water, okay? And we make a cake. Well, if I mix all of those things together, a cake is not going to magically appear. I have to put it in the oven. And when I put it in the oven, I turn the oven on, it adds heat to the ingredients. Okay, so energy, so we would just say plus energy. Okay, energy is an ingredient almost. It's a reactant. You have to have it in order to produce that cake. An exothermic reaction is the opposite. Energy is a product. So you have your reactants that break down into your products, if I could spell, plus energy. Okay, and an example of this is anything that catches on fire. When you catch on something on fire, you have, right, like wood and things like that, and it breaks down into ash, smoke, and heat, right? You feel heat when wood is burning. Okay, but you say, well, in order to get the wood to start, being on fire, it kind of takes a little bit of energy, right? Like you have to be able to you gotta create a spark, things of that nature, okay? And that brings us to our next topic, okay, which is what these graphs look like. Okay, so if I'm looking at a exothermic graph, okay, of a reaction where we have energy on our y-axis and time on our x-axis. Okay, exothermic reactions start off with a lot of energy. Okay, they start here. And for example, creating a bonfire, we put in a little energy, right? We got to organize it in the right way. We have to maybe put some gasoline on it, create a spark, right? We put a little bit of energy in. And then once we reach the top of our hill, the reaction starts to happen. But all of a sudden, we release a ton of energy. Okay, we go down, and we end up down here. Okay, we draw an arrow from where we start to where we end. Okay, it's decreasing, which shows us that Q is negative. Okay, and in this case, that's also going to be the same as delta H. Okay, so even though we put in a little bit, which the space from the top of the hill to where we start, that's called our activation energy, which is the amount of energy required to get the reaction started. So it has a small activation energy. If we look at the graph for endothermic, it's very, very similar. Energy on the y-axis, time on our x-axis, except it's kind of like the opposite. We start off really low, okay? We absorb a lot of energy and then we release a little bit, okay? And so my activation energy is from here to here, okay? And I'm going to abbreviate activation energy as EA. All right, so my activation energy is huge for endothermic, and how much is released from the top of the hill to the end is very, very small. Okay, and if I draw my arrow from my start to my end, like I did before, it's now increasing, so my Q is positive. So then let's look at phase change diagrams. Okay, so we have phase change diagram. So I'm trying to do this quickly so you don't have to watch a crazy long video. But with phase change diagrams, okay, they look like this, okay. They kind of have like a weirdly shaped Y. Pressure is on the y-axis and temperature is on the x. In this region we have solids, and then liquids are in the middle, and gases are over here. This point in the middle, that's our triple point. Okay, and the triple point is where you can see all three phases at the same time. This point here is called our critical point. And we're going to have blue is going to be endothermic. Red is going to be exothermic. In order to go from a solid to a liquid, you have to put energy into it. And so melting is endothermic, while freezing is exothermic. Going from a liquid to a gas is vaporization, and that's endothermic. Whereas going from a gas to a liquid is condensation, and it is exothermic. And going from a solid directly to a gas is sublimation, and is endothermic. While going from a gas to a solid is called deposition, and is exothermic. Okay, those are the main things to know about phase change diagram. Now we also talked about a few other types of graphs. We talked about heating curves. Okay, with heating curves, looks kind of like this. Okay, where we have ice or solids melting, and then it becomes a liquid, and then it starts to vaporize or boil, vaporization, and then it becomes a gas. Okay, now I forgot to put that temperature is on the y-axis, and time, although sometimes you see it as energy, this is really both, is on the x-axis. Okay, now if this is for water, ice starts to melt or liquid starts to freeze at 0 degrees Celsius, and vaporization happens at 100 degrees Celsius. Okay, and the reason why these two lines are flat, even though clearly we're moving forward, we're adding more energy, but the temperature is not increasing. The speed of these molecules are not increasing. It's because the energy is used to break the intermolecular forces of the phase. Okay, so we know that if we look at solids, right? Solids have all their atoms really tightly packed. Okay, and it's because they have these strong intermolecular forces that basically it's just this interaction, like these two atoms are close by each other and they're really, really attracted to each other. They have this force and it's holding them really, really close. Well, if we put enough energy into it, eventually things will start to melt, right? And then when it becomes a liquid, those atoms are a little more spread out, but it's kind of like a bungee cord, right? You can only get so far. Okay, and vaporization is longer than melting, that line is, because it takes more to completely break all the intermolecular forces so that gases can spread out. Okay, that's kind of what we want to learn from that. The next thing is specific heat. Oops, let's get our nice bold. Okay, so specific heat. The symbol for specific heat is a capital C. Okay, and it's the energy required to raise temperature of 1 gram of a substance by 1 degree Celsius. Okay, and so if we have, let's think for a moment about just a little mental picture here. Okay, let's say we're at the beach on our little island and we have some sand. Okay, I'm gonna draw my little picture here. Okay, and this sand is so nice and we're having a good time at the beach. Okay, we got some palm trees that are real nice, just some palm trees, yay. And at the beach, we got some nice blue water. Okay, now I think I'm using this example because I really can't wait for the summertime. But we're on the beach and the sun is out. Oops, that's not yellow. The sun is out and it is shining. It's wonderful heat waves on us. Okay, so we got the sun. Well, what's happening is we're walking on the beach, right? Well, let's say my feet are burning, so I'm not happy about that. Well, if my feet are burning, am I going to walk on the sand or am I going to walk where the water? You probably hopefully said the water, right? Because the water feels cooler on your feet. But what if I tell you the sun is giving off 500 joules of energy? Well, if both the sand and the water are getting the same amount of energy, why are they not the same temperature? Right? Like, why aren't they the same temperature? Well, water has a specific heat of 4.18 joules per grams degrees Celsius. That means in order to increase the temperature of water by 1 degree, it needs 4.18 joules. But for sand, the specific heat is somewhere around like 1.5, I believe, joules per grams degrees Celsius. So that means instead of needing 4 joules to increase the temperature, it only requires like 1.5. So sand is going to increase by a much higher degree. It's going to increase much faster because it has and requires less energy to heat up. Okay, so this explains why the concrete around your pool is so hot, but your water in your pool is nice and cool. Okay, so this explains it. So low C number means things heat up and cool down quickly. Okay, so because water has a pretty large specific heat when compared to other things, it heats up. So, oh, let's erase that. It heats and cools slowly. Okay, because that number is so much bigger. Okay, Now, with specific heat allows us to calculate how much energy was absorbed by something by using our formula Q equals mc delta T, where Q is our heat, okay, and it's measured in joules, which is a capital J. Our M is our mass, which is measured in grams. C is our specific heat, which is measured in joules per grams degrees Celsius. And delta T is change in temperature, okay, and it's measured by your T final, your final temperature, minus your initial temperature, okay? And so if we do problems like this, all we need to do is plug in our information to solve for whatever variable we're using. And there are sample problems like that in your notes and on eClass. But when we go back to our heating curves, okay, it also allows us to calculate how much energy was used in certain situations. So A, B, C, D, E. All right. Now, we talked about how B and D are those flat section, those phase changes. And there's this thing called H. I mentioned it earlier. H stands for enthalpy. Okay? And it's basically the energy needed for a specific phase change. Okay? So as segment B, we are melting, right? And so we call that delta H of fusion. Now, why it's fusion when melting is kind of coming apart, but fusion is coming together, I don't know. That's just, it is what it is. Okay? Whereas at segment D, we're vaporizing, and so the energy required for vaporization is called delta H of vaporization. Okay? But in segments A, C, and E, we don't really have a phase change going on, and so all of the energy is being used to increase the temperature. So we have two different formulas that we use. So in segments A, C, and E, we use our Q equals mc delta T formula. And in segment B and D, we use Q equals m delta H. Now, if I want to find out the amount of energy required to go from A, so like let's say negative 10 degrees, all the way to 125 degrees, I'd have to heat up all my solid ice first, then melt all my ice to a liquid, and then heat that liquid up, boil and vaporize off all that liquid, and then heat up that gas to the 125 degrees. Okay, so that means our Q total would be equal to QA plus QB plus QC plus QD plus QE, all of our segments added up together. So hopefully that kind of jumpstarts your brain. If you need math problems, math help with that, you can come see me in the morning or tomorrow afternoon for tutoring. But also you've got notes on eClass for that and from class. So good luck on your test.